Okay, I guess everybody's here, more or less, so I can get started. So far we've been covering sort of background material before really getting into transforms, and today I'll continue with background material, mostly about the impulse function, discrete and continuous time convolution, introduction to signals, and then try to give you an intuitive understanding of the complex exponential signal, which is why I have that printout that I brought with me. And then next time we'll continue with sort of our first real understanding of systems and linear time invariant systems, which will set the stage for transforms. Okay. So there's a chair over there in the back. Okay. So let me start with this discrete and continuous time convolution. I'm going to, as I mentioned, the signal is just a series of numbers, and we kind of don't really care where the numbers came from, but just for the sake of concreteness, think of some web server, and we're trying to measure the number of requests that come every second. So we have some server, and it's getting requests from the web, and so we're going to have some number of requests. So every second we just count how many requests came in, and you have like one. I just have this number in the example over here, 1352, and so on. So it's just a set of requests per second. It doesn't really matter what it is, but what we're seeing is this notion of a discrete quantity which is associated with a time step. So we're getting that, and we can draw sort of a not quite a histogram, but it's basic. Well, you can call it histogram. At least I call it histogram. A histogram has a specific meaning in statistics. Here I'm just talking about a discrete function of time. So I'm using the word histogram not in the right way, but anyway. So it's 1, 3, and then 5, or something like that. And let's say that's 2, and so on. Okay. So it's a discrete function of time. The intuitive understanding here is that we can represent this as a sum of separate functions. So I can take this as being the sum of something which is 1 and plus, where plus I haven't really defined what plus means, but intuitively it's like you're adding these things together in some fashion, and and so on. So what I'm trying to indicate over here is that we can take any function, any discrete function, and view it as a composite of multiple underlying functions. Okay, and that's intuitively what we're trying to do when we are going to work with the impulse functions. So we have two operations going on. One is sort of a selection of a particular time step, and then we have the composition of the selections. Okay. The composition is not as important as the notion of selection. So I'm going to focus on selection for now. So what I want to do is, given a particular time series, which is what this is, I want to pick a particular element of it, okay? And that element is what I want to focus on, okay? So that's the intuition over here. So let's see how to do that. Let's say that I have a function which I call selector, okay, and I'll just call it cell t tau, and this is defined to be 0 if t is not equal to tau, otherwise it's 1 if t equals tau. Okay, so for some reason I've decided to give it 2 parameters, not 1, but I'll see in a minute why that is. And it's saying that if these two arguments are the same, then it's 1, otherwise it's 0. So it's just a definition of the way I'm setting it up. And so what we can say is that at any point in time, xt is going to be given by just the product of xt and cell t tau, okay? Because this one is going to be 0 other than when tau equals t. At that point, it's going to be equal to, actually, what am I saying? It's okay. Oops. I can rewrite as, some So I can write this as this. So essentially this summation is giving me nothing. Okay, this summation is kind of a bogus summation at this point, because the only value of tau that makes sense is when tau equals t. At that point, cell just drops out as being 1, right? And then you get xt equals xt. So I'm just rewriting xt in a funny way, okay? But I'm not doing anything special here, okay? The summation here is formal, I guess. It's just to show a particular operation, but again, it's not doing anything. I'm just saying I can rewrite it like this, like saying I can add 0 to a number and add 0 to a number. You know, I'm just doing something because I want to set up a particular form. Okay, so I'm not changing anything. So is this clear? I mean, certainly this operation is mathematically valid. Okay, for this value. So, okay. Any questions about? Because this form becomes important later on. So I just want to show you the form. So all the form is saying is that I have. So you can think of it as I'm multiplying all the elements of this function with 0 except the value at t, which I'm going to have multiplied by 1, and everything else. So I'm selecting out the particular value of xt, okay? Because so everything else in the summation drops out to be 0. Okay. All right. So now the second question is, okay, how do we get this cell t tau? And so we need to first look at this notion of what is the meaning of a time shift. So let me just, and it's kind of obvious once you stare at it for a bit, but it's not so obvious when you first look at it. So let's look at any function, and let's just take a very simple function over here, which is a discrete function. I'll just say it's 1, 2, and 3. And let's say this is a time 1, time 2, and time 3. And okay. All right. Now, and I'll say x1 equals 1, x2 equals 2, and x3 equals 3. Okay. Now I want to look at the function x t minus 1. Okay. Well, let's say this is xt. This function is xt. Okay, so we just, plug and chug. So when t equals 0, then this is equal to x t minus 1 equals x minus 1, which is undefined. And we'll make the assumption if it's undefined, it's equal to 0. So this is equal to 0. And then if t equals 1, this is plus x t minus 1 equals x 0, which is also undefined, so it's still 0. T equals 2 is x 2 minus 1, which is going to be x1, which is, we know over here is 1. And then t equals 3, you get x2, which is equal to 2. And then t equals 4, you have x3, which is equal to 3. Okay, just from this table over here. So if this is xt, this function is x of t, then xt minus 1, just from drawing it out, is going to be same thing, 1, 2, 3, except the time index is not going to be 2, 3, and 4. It's just this table over here. It's 2, 3, 4. Okay? It's no magic. It's just this. So if I take the time value and I subtract 1 from it, it's just this one right shifted by 1. Okay, in general, if I'm going to subtract a from this, or whatever quantity t minus a, then it's the same xt shifted right by a time steps. Okay, so subtraction over here is time shifting it, okay, to the right. Okay, so we can just say that x of t minus a is equal to xt time shifted by a steps. Okay? Any questions about that? So we just kind of just mathematically saying, yeah, I can take a function and shift it. All right, so now this gives us some intuition into how to select different parts of this function, because remember what I wanted to do was to select this and then select that and then select that to kind of decompose it. So I want to figure out a way to decompose it. I need to move a selector around, and the way I move the selector around is by doing this over here, but I still haven't shown you what a selector is. Okay, so now I have the second thing that I want to define, which is called the delta function or the impulse function. And it's defined like this. We say that delta t, okay, so delta of 0 equals 1, and delta t equals 0 for all t not equal to 0. In other words, it's just like a function like this. At 0, we have sort of a value of 1, and then the rest in all directions is just 0. So by 0, we mean the interval 0 to just before 1, right? So kind of assuming that convention. So it's that's what it is. That's your delta function, the discrete delta function. Get rid of this. Okay, so now we almost have everything we need. We need to take delta, and we use this time shift, and then we can kind of select wherever we want, right? We can kind of move it around by subtracting from it. So if you want to select the third time step, that will be given by delta t minus 3 is going to be essentially delta minus 3. What am I doing over here? Delta t minus 3 is going to select sort of the function xt sort of 3 time steps away, because this is going to be this is going to be 1 when t equals 3, and it's going to be 0 elsewhere, right? So this function is going to be 1 only when t equals 3, the third time step, and everywhere else it's 0. So if I were to multiply delta t minus 3 with xt, okay, I'm going to basically get x of 3, okay? Because everywhere else it's going to be 0, which is, and you can view that as basically t equals 3 or tau equals 3. It doesn't really matter, because at any rate x3 is all we care. We're selecting the third element from. Okay, so I'm going to go back to this here, because we have the cell t tau, and we have this over here. So now we can say what cell is. It's going to be nothing more than, again, this is form that I want, t equals infinity to 0, x tau, xt delta t minus tau, okay? Because I've shown that the selector, which is selecting the tauth element, okay, is nothing more than the t minus tau applied to the delta from the definition of the delta. So again, we view this as this delta is selecting, is 1 when t equals tau, and is 0 otherwise. So it's selecting the tauth element. And so all the other elements of the summation follow out. So we're always saying is xt equals xt, but I have that form over there, okay? So we say xt equals. Any questions about this over here? Yeah?
How is from infinity minus infinity to 0?
For right now, I'm saying 0 to infinity. This is for signals which have a value of plus only in the positive range, which is most what I call causal signals. But as I'm going, in the next step is to say, okay, this is going to be equivalent to tau equals minus infinity to infinity xt delta t minus tau, because anything it's in the negative range anyway, xt is 0. Okay, when it's undefined, we just call it 0. So I can certainly make it minus infinity, and so that's exactly the next step in this process. Okay. Okay, so this particular form is a very important form, and it becomes important when the function we're looking at is not just a delta function, but arbitrary function. So I'm going to write down, where do I want to do this? Okay, I want to keep it on this side. So I'm going to, I wish this were at the top. Okay, I'm going to leave this here. I'm going to just write down over here the discrete convolution of xt and yt Okay, let's say zt is this is equal to zt is given by, is written as xt and this funny symbol xt convolved with yt. Okay, and is defined to be, and we use this usually means defined to be, so triangle with equal to, it's defined to be tau equals minus infinity to infinity x tau delta t minus tau. Okay, so one thing I missed over here is that since we have xt, it only has a value when t equals tau, we may as well put tau over there. So I'm just going to do it right here. I'm just going to put that tau x tau delta t minus tau. And then we find that this can be viewed as basically x multiplying with the, x and delta. I'm going to replace delta with y, and I'll call this particular thing the convolution, and it's x tau delta t minus tau. Okay. So I'm kind of going around this in a fairly complicated way. So the intuition is initially that all I'm trying to do is to select a piece out of a function and then assemble it in this fashion. But now I've made a big step. I've said, well, it's not just for the delta function, which is selection, but actually I'm going to do it for any function y. Yeah?
Shouldn't there be y?
Oops. It should be y. Okay, so what I'm doing is for any function y, I'm taking x tau yt minus tau, and I'm going to compute this zt as the convolution of x and y. Okay, so the difference when you do it this way, when you do delta, is the delta has value only at one point. Okay, which is or one time interval like so, but y could have value over any time interval. So this convolution turns out to be a bit more complicated. Okay, so we've kind of made a step here, a fairly large step, to go from this very simple-minded delta to having any arbitrary function y, and to kind of fix ideas, I'm going to show you the convolution of example. This is also your homework, and that will give you hopefully a better idea of what we're doing over here. So I haven't quite told you why we care about convolutions and so on, but when we talk about systems analysis, it will become clear why the convolution operation is important. But right now we're sort of just going through the mathematical description. This is like determinants. I'm telling you what the determinants are without telling you why. Okay, and you see later on it's useful. So this is useful, so we're going to go through it. Okay. So any questions about this derivation over here? So I went from cell selector to this definition, which is just a form, to this definition where I've replaced cell with delta, the impulse function, and then here I've taken to change the limits and also changed the variable from t to tau. And then from here to here, I've said, okay, I can do this not just for delta, but I'm going to have this. Of course, if I do it with y, I don't get xt anymore. I get something else. I get zt, and that's the form. Okay? Okay, so let's do an example of this. And I'll do the one from the homework. So the question was, we want to convolve these two discrete functions. So xt, 1 less than equal to t less than equal to 8 was given by 1, 2, 5, 7, 3, 9, 4, 6, and then yt 1 less than equal to t less than equal to 8 was given by 2, 3, 1, 5, 5, 9, 7, 2. So let's see how to compute zt. So let's see what is z1. Okay, z1 is going to be minus sum from minus infinity to infinity. Okay, so t equals 1, and we just plug in the definition. It's going to be x tau yt minus tau. So x tau equals x tau y. T minus tau is 1 minus tau, right? Okay, so well, when tau is less than 1, x tau is going to be 0 because x is only defined in the range 1 through 8. So tau is less than 1. So we don't really care about that range. It's just going to be basically tau equals 1 through positive infinity, x tau, y 1 minus tau, right? And let's look at the y. Well, when tau is greater than 1, this is going to be y0, right? And then when tau is 2, it's going to be y minus 1 and all that stuff, right? So that all goes away, right? Whenever tau is greater than 1, y1 minus tau is going to be 0. So the only value that we care about is basically sigma, tau equals 1 to 1 x tau y 1 minus tau. Oh wait, am I doing this right?
It's going to be an empty sum.
Yeah, so this is going to be actually 0 because this is going to be y0. So it's just going to be 0. Okay, z1 is not going to be, because there is no value for which they're both simultaneously going to be non-zero. Okay, yeah.
I think the range from 0 to 8 is out of 1, right?
If the range is 0 to 8, it would be a different question. But I put it in the online. I just changed it from 1 to 8. So we're going to do it for 1 to 8. Okay, because that's this question as stated. So z1 or z1 is going to be 0 because there is no value for which it's going to work, right? Okay, so let's try z2. So z2 is defined to be sum tau equals minus infinity to infinity, x tau, the same thing, y 2 minus tau. So let's see, first apply the value for x. So x is going to be 0 other than, so tau has to, lower value of x is going to be 1, right, to infinity, x tau, y 2 minus tau, right, because on the bottom level, if x is not equal to 1, you're not going to get anything. And then on the above, what we see is that when tau is greater than 2, we're out of luck. Even tau is equal to 2, we're out of luck. Only tau equals 1 makes sense. And so this is going to be sum tau equals 1 to 1, x tau, y 2 minus tau, which is going to be equal to x1, y1. And this finally we can solve as being equal to 2. Okay? So the first term z1 is equal to 0, z2 equals 2, and then z3, I'll just write out the steps, is going to be again minus infinity tau equals minus infinity infinity, x tau y 3 minus tau is equal to sigma tau equals 1 to infinity x tau y 3 minus tau is equal to sum tau equals 1 to 2, because it's 3 minus 2. After that you get 3 minus 3 and so on. X tau y 3 minus tau, that's equal to, well, x1 y 2 plus x2 y 1. And that we can finally do as 3 times 2, 3 plus equals 7. So the first 3 terms are going to be 0, 2, and 7. Okay? So some of you may have gotten 2, 7, and 17, and that's wrong. Okay? Because that's Z4 is 17, not Z3. So I wanted to get you the first 3 terms. The first 3 terms are going to be in this range 1 through 8, right? Because x and y define as, yeah.
In general, they usually start with t equaling 1.
T can be 0, 1, whatever, it's arbitrary definition of what the base is. But we want the convolution to be defined in the same range as the functions. If the functions define 1 through 8, then z should be defined in the range 1 through 8. But certainly it's true that z1 is going to be 0, no matter what the range of, the range of definition is what's over here, right? So you can say, yeah, z1 is not 2. z1 is 0. Okay, you can say, yeah, z2 is 2, z3 is 7, and z4 is 17. That would be fine. Yeah?
I think if we define it from the 0 to 7,
yeah.
then and the first element won't be 0.
That's
Because you're actually shifting both of them one element to the right.
Yes.
So the convolution will be shifted 2 times. So that's why you're getting the...
I know. But I'm giving you, I want you to think. I don't want you to blindly apply what you learned from convolution in the undergrad or wherever it was, right? You need to look through the definition carefully and go through it. Yes, you're right. Normally the definition would be 0 through 7. But I put that specifically, and I should have put it in the original question for that reason. But that's basically what we want to do. Yeah?
Was it the time range defined?
Yeah, I added it because somebody asked the question, what range is it?
And when was it?
It was a few hours after the question was posted, I think, and so I modified it right away to say. In fact, I made a mistake. I said 1 is less than equal to xt less than equal to 8. What it really meant to say was 1 less than equal to t less than equal to 8, and I think somebody pointed out that I made a mistake. But the range is 1 to 8. Okay. So don't worry if you lost a mark. It's not a big deal, okay? But what you are hopefully learning is that you have to be really careful, okay? You have to be very careful when you do convolution. Yeah?
What about Z9? Are we saying that 0 also?
Z9?
Yeah.
I just wanted the first 3 terms.
Yeah.
Oh, okay, so what is Z9?
Is it 0? Or because if you do the math, you get some non-zero value.
You get, yeah, so...
The range therefore 0?
So I don't know. I mean, the thing is, it'll turn out that the range of the convolution is going to be larger than the individual ranges. It's possible, right, for the range to be larger. In fact, almost double. So it's a question of what do you want exactly. So the kind of rule of thumb is you added the indices when the indices sum up. If they're in the range 0 to n, then the indices sum up the right way.
That's what I was asking you. What do you want? Or will it depend on the context?
It depends on the context, and honestly, it's kind of up to when we talk about convolution, we are usually interested in trying to solve the system. Okay, we're trying to solve a particular linear system, and so the convolution will turn out to be the response of the system to some input. Okay, in fact, the impulse response is what you so that will have some meaning going beyond the values of the inputs itself. So Z9 would have a meaning in that context. But right now we're not going into that. We just want to focus on the math. So these two equations are sort of the important equations. And I'll just quickly show you what's going on. Basically, this one says that I use the impulse function to select out the tauth element of x tau and everything else doesn't matter, so this turns out to be xt because everywhere else, tauth element is going to be the tth element of xt, okay, so that's what we get out of here. And this one generally defines zt to be this particular value, and the thing to be careful about is the range of definition of x and y. Let's try and carry this over to the continuous case, and in the continuous case, life is quite hard. Quite a bit harder, and the reason is because whereas the discrete case I kind of knew what to do. I had this selective function which is just this 1 here and 0 everywhere else. I had this notion of a time step. I had this intuitive notion of a histogram that I could appeal to and say that this is where it is. But in the continuous case, if I define a function to be 1 in just one single point, there's some point t, and over here the value is exactly 1, and everywhere else it's 0, this function is mathematically terrible. Okay, it's discontinuous. So we have 0, 0, 0, 0, 0, boom, we shoot up to 1 and then come down again, and off we go. And discontinuity upsets mathematicians because then you can't do calculus. And if you can't do calculus, life is not good. Okay, a lot of mechanism depends on calculus. So mathematicians will go through a lot of trouble to avoid discontinuities. Okay, so ideally we want this, but we can't have it. We can have it, but then it's not going to allow us to do good math. So people tried various things, and then Dirac, who was a physicist, actually not a mathematician, Dirac proposed something called the delta function, and so it's named after him. It's called the Dirac Delta, and it can be viewed as a limiting case. I'm just going to draw it like this. So I have over here a function which has a span of, let's say, capital T, and the height is going to be 1 over T, so that the area is going to be just 1 over t times t equals 1. So it's a unit area. Okay, so that's the, now I'm going to make this shorter, the t smaller, so I get a taller one. It's still t 1 over t, and I'm going to make it smaller yet. And so we have like this one as unit area, whoops. And then I go here, and then this looks really skinny, and it's so thin I can't draw anything. But it's shooting up higher and higher. It's not at 1, right? It's not at 1. It's going up higher. In fact, in the limit, the base is 0, but the height is infinity, and the product is 1. Okay, and you say, how can you multiply infinity by 0 and get 1? And the answer is, you can't, you know. But you can approach it. You can approach it as a limit. So we have a limiting series which goes like this, okay? So basically, t tends to 0, right? And we have an area of 1 over t, so it gets taller and taller. So the area is always 1. The area is conserved, right? And so we can take t as small as you want. It can be a, a picometer, which is really, really tiny, and then it will be 1 over a picometer, right? Which is a terameter long, okay? So picometer narrow and terameter long, and I think that it matches up, 10 to the minus 12, yeah. 10 to the 12 times 10 to the minus 12, so that will actually match up, and you get something that's, in this case, 1 square meter unit area. And so we can imagine it, even if it's kind of bizarre. But the nice thing is it's a continuous function, okay? Because I have this continuity of this function like so, right? I don't have I don't have this notion that it's discontinuous, okay? I can kind of go up, and then I have corners, but still it's continuous. And so continuity being preserved, we can do calculus on it. And what is the limit? The limit we don't know. The limit is infinity times 0, but we can compute the properties over here and over here and over here and so on. And for the limiting, we can kind of guess what it's going to look like at the limit, okay? So we can have this, the properties of the delta, the Dirac delta, computed for non-zero values of t, and we set t to 0, and in the limit we say, yeah, this is what's going to happen. And this is what we're familiar with in calculus anyway, right? When we talk about calculus, we assume the notion of an infinitesimal, and then we do all the work in infinitesimals, and then we say, yeah, delta over delta, delta over delta equals 1, okay, and this is true when delta equals 0, okay, or delta tends to 0 actually. We just cancel it out, because we know it's equal to 1. Well, if somebody asks you what is 0 over 0, well, I can't tell you that. But delta over delta is equal to 1, 3 delta over delta equals 3. So we're perfectly happy working with infinitesimals, and the mental assumption that the limiting case looks like the case when delta is not 0, right? So we have this notion of limits. So all this is by way of saying that the definition of delta, of Dirac delta, is mathematically can be made very rigorous. Okay, it can as a limiting series, but that development is something that I don't want to go into. Okay, so now we're going to put on our engineering hat and say, all right, fine, the mathematicians can make it as rigorous as we want. What is the practical use for it, and what can I do with the delta? And so I'm going to give you the definition of Dirac delta from an engineering perspective, and just say, okay, this is what it is, and we can make it formal if we want to, but we won't. Okay, and the definition of a delta is defined to be integral minus infinity to infinity delta t dt equals 1. So the area under the curve is 1. So that's why I said it's unit area. And the second is the delta t equals 0 for all t not equal to 0. And delta t at 0 is basically undefined. Okay, but we don't need to say that. For all t not equal, we know it's definitely 0 when t is not equal to 0. At 0, something magical happens and the area becomes 1. Okay, and that's the limiting case. Okay, so I'll kind of give you a small story about this. Physicists and mathematicians, generally speaking, don't like each other in the following sense. The mathematicians want everything to be just nice and precise and kind of just right. Everything has got to be axiomatic. The physicists are dealing with real systems, physical systems, and so they take shortcuts all the time. They say, yeah, we'll kind of just assume things are like this, and if it works out, that's good. Okay, and if you look at Newton's work, Newton's Principia Mathematica, it's full of these shortcuts. Okay, it's full of all sorts of, he just played with infinitesimals, you know, as if they were real numbers, and it was appalling. I mean, if you look at the stuff, a mathematician today looking at it say that's